Welcome to AP Physics review of rotational motion. So here you have a summary of basically all the equations rotational that I'm going to briefly talk through. Then we're going to talk more in terms of conceptually definitions, get into some things with right hand rules, get into some things with equilibrium, get into some overall things with rolling motions and linear and circular and rotational motions. So here we go. General average equations for rotational motion. Omega is delta theta over delta t. Alpha is delta omega over delta t. All of your symbols I summarize down here if you need a refresher on any of the symbols, any of the units. So then back up to our average equations. You're going to apply those equations anytime you're looking for average values or not instantaneous values. If you want instantaneous values, you're going to have to use the motion equations, which only apply when you have an object that has a constant angular acceleration. If you do not have a constant angular acceleration, then you're going to have to apply the calculus equations here. Relating linear and rotational motion, right there. Your units do have to be in radians for that, and pretty much everything, the rest of the relationships over to the right of that, you will need to be in radians. It's only really your average equations and your motion equations that will work for any units. Rotational inertia. Key thing to remember here on rotational inertia is that every rotational inertia is dependent on a mass and a radius, an mr squared term. It's not very likely that they're going to have you derive any moment of inertia based on the format of the exam this year, but you do need to know what they are dependent on, and when you're thinking about the rotational inertia, think about where the mass is and how much mass you have, and we'll talk more conceptually on that in just a minute. Your torque, the thing that changes the rotational motion of an object. There's your base torque equation, R cross F, and then Newton's second law, net torque equals I alpha. And then power, parallel axis theorem. Remember, parallel axis theorem is something that you use if your object is not rotating around the axis that is defined by one of these equations. So if you have to adjust the position of the axis, then you're going to use the parallel axis theorem, and you're going to tack on an extra md squared term, where d is the distance from the center of mass, okay, out to where the given axis is. And on those equations, just remember, it does not apply. Parallel axis theorem cannot be used on that one that I'm trying to erase because your axis is at one end, not through the center. Angular momentum. If it's a particle, it's an R cross P. If it is a discrete object, then it is an I omega. And then you have situations where angular momentum is going to be conserved. Li equals Lf. Situations where it changes, where you have an angular impulse. Torque delta T equals I delta omega. Now, let's dive a little deeper into the concepts here. So, radians. Radian is basically a radius length of rotation. So in the circle I have drawn there, I have the radius shown. If we picked up that radius and we wrap that radius around the arc, it would stretch out to a certain location. So when you have one radius wrapped around the arc, then that central angle, that theta, would be equal to 1 radian. So then if you continue to wrap radius lengths around the arc of your circle, if I wrapped another one, and another one, by the time I got about halfway around my circle, we would have a little more than 3.14 or pi radius lengths. That takes you about halfway around a circle. A little more than 6 or 2 pi radius lengths take you all the way around a circle. So that's really where your equation S equals R theta comes from. S is the linear, that's the arc length, and theta is your angular, that is your number of radians. So when you have like 5 radians, this is basically telling you wrap 5 radius lengths around the circumference or around the arc of a circle. Moment of inertia, that's probably the term they're going to use, okay, as opposed to rotational inertia. Moment of inertia, property of an object, just like a regular inertia. Resistance of an object to change its state of rotation. Basically, spinning objects tend to continue to spin. If I had the bike tire in my hand and I started it spinning, it's just going to keep on spinning. Remember, it depends not only on the mass, but also on the radius squared. And we did the experiment in class whereby I had a couple of cardboard tubes, and one of those cardboard tubes had masses here towards the middle, and one of those cardboard tubes had identical masses out towards the outer ends. When the mass is farther out, it is harder to rotate. And when it is harder to rotate, that means it has a larger moment of inertia. Where the masses were towards the center, closer to where you put your hands and you pivoted, okay, that's going to be easier. And if it's easier, it has a lower moment of inertia. So when you're considering a rotating object, always look at where the mass is and how much mass is there. That's going to determine the inertia, determine how hard or what torque is needed to change the angular acceleration or spin the object. So then torque, quantity that changes the rotational motion of an object, is basically your rotational equivalent of a force. Extra force, extra newtons, speed an object up linearly, slow it down, or change the rotation, the linear motion. Extra torque changes the rotational motion of an object, and that's where our Newton's second law equation comes from that we pondered just a second ago. Now your base definition of torque, torque equals R cross F. On the diagram there, you've got the radius from the pivot out, and then the force, and so theta is the angle between your vector direction of R and your vector direction of F. When you're applying the cross product, make sure it's R cross F, not F then R, because you'll get your vector direction wrong, but we'll talk about right-hand rules in just a second. Angular momentum. In class, we had the bike tire. I had each of you hold it, holding onto the handles, and then I spun it. And then you tried to rotate it, change the axis, and it fought against you. That's what angular momentum is. It's that fight of an object to maintain its axis or its angular velocity vector. You change that when you apply an external torque, like you did when you were holding the bike tire. More exactly, that's an angular impulse, but either way, it is something external. Angular momentum is constant when the net external torque is equal to 0, and you only have internal changes. For example, an ice skater is spinning. They start with their arms and a leg out, and as they spin, they pull them inward. That is an internal reconfiguration of mass. An external would be they're spinning and somebody walks by and pushes one of their arms to get them to spin faster. That would be an external impulse. But any internal reconfiguration, the total angular momentum is conserved. When an ice skater moves their arms from being out to in, out they have a high rotational inertia, in they have a low rotational inertia. When their arms are out, their omega is little. When they pull their arms in and reduce their rotational inertia, then the balance goes to the angular velocity and they spin faster. By the same idea on the spinny pukey ride on the playground. If you hop on the outer edge, and then you move your body from the outer edge to the inside. When you're moving to the inside towards the center, that's an internal reconfiguration. And so the ride will spin faster, but the angular momentum is conserved. Right hand rules. Angular velocity. Wrap your fingers of your right hand in the direction the object is spinning, and your thumb will point the direction of the angular velocity vector, and it will be along an axis. If your object is speeding up or slowing down, the angular acceleration vector is either going to be in the same direction as the angular velocity vector if the object is speeding up, or opposite to it if it's slowing down. So you have to find the angular velocity vector first and then see what the object is doing. Torque, the R cross F. Fingers in the direction of R, wrapped into the direction of F as shown here. Your fingers would point that way. You would then bring your fingers down to the direction of the force, and then your thumb is going to point the direction of the torque vector. It is again always along an axis. Theta then is the angle between that R and that F. Keep in mind that your sine value, whether you take the angle I have drawn there or right here, I can't call that theta, that angle, which would be the supplement of theta, your sine value is going to give you the same value whether you use theta or the supplement, so either one is fine. Angular momentum, L equals R cross P. Same idea as your torque right hand rule. Your fingers are going to point in the direction of R. You're going to then wrap them to the direction of P, which P is equal to mv, so you're wrapping to the direction of the velocity vector. And then your thumb's going to point the angular momentum vector, which is again along an axis. If you're using L equals I omega, wrap your fingers in the direction of the spin, and your thumb is going to point the direction of the angular momentum. Equilibrium. We talked about translational equilibrium, and that's your normal linear equilibrium where you have no extra newtons. So there is no change in the linear motion of an object, no acceleration. Your object is coasting. It's doing what inertia does. It's maintaining. So you have no extra newtons. Net force is equal to 0 is the mathematical condition. Rotational equilibrium. Now your object is spinning, but it has no angular acceleration. It's not spinning faster, it's not spinning slower, or it's balanced. So no change in the rotational motion. The condition then is no extra torque. The net torque is equal to 0. You then put those together to get total equilibrium. No extra force, no extra torque. These are typically systems that you would not expect to rotate, okay? And because they are not rotating and shouldn't rotate, you can mathematically put the pivot anywhere that you want. So place it somewhere that is easy for calculations. For example, the two situations below, you have a bridge that's supported by two pillars. The pivot here, I could place the pivot anywhere I wanted along here. But if I put the pivot, for example, right there under F1, then in my torque equation, that's going to eliminate the torque from F1, and I can immediately solve down for F2. Another situation. You have an object that's leaning. For example, here, a ladder leaning against a wall. If we draw the forces that are there, first of all, I would have an F1, and that would be basically a support force or a normal force supporting the entire ladder. I would have the weight of the ladder, an mg. I would have probably a frictional force keeping it from sliding. So we put a frictional force there. And then I would have the force of the wall pushing against it. There may also be a vertical force between the top of the ladder and the wall, a frictional force, but that would be dependent on what's given in the information. But on here, probably depending on what we were finding, I would take the pivot and place it down there at the bottom, because that's going to eliminate a couple of forces and make my situation a little bit easier to be able to deal with. Rolling motions. When you have a rolling motion, it's a combination of a linear motion and a rotational motion. So on my two wheels that I have here, linear motion, this is just moving straight across. Rotational motion, now we have this object that is spinning. A rolling motion is a combination of those two different motions. So I'm going to pull this back here. If we identify velocities, center of mass there in the middle. So when you have just a linear motion, that's just the entire object moving at one velocity, the velocity of the center of mass. All points move at that velocity. When you have a rotational motion, you have that spinning motion, then you have the outer edges moving, and so I would have a velocity here, a velocity there, okay, and when you're at the outer edge, that velocity will match the velocity of the center of mass above if it is a rolling motion. So then you put these two together and you get that rolling motion, and that's where your equations S equals R theta, V equals R omega, and A equals R alpha. Connect those two motions between the angular and the linear. For linear, circular, and rotational motion, you have to be able to distinguish circular motion from rotational motion. Circular motion is like a tennis ball on a string flying around in a circle. It's the object where all of the mass is essentially doing exactly the same thing, moving at exactly the same speed. Rotational motion, that's a spinning, and you don't have everything moving at the same speed. For example, on my wheel over here, the different points that I'm drawing, they're going to be moving at different speeds. Towards the center, it's going to be moving slower. As I move outward, my velocities are going to get larger and larger, and that's, again, where you can use this equation to be able to connect. They all spin at the same number of radians per second, but they do not move at the same number of meters per second. So when you have that spinning motion, you have a rotational motion. Now, to be able to connect them, we have different accelerations. We have an A sub c, a centripetal acceleration, we have an A sub t, a tangential acceleration, and we have an alpha, we have an angular acceleration. Okay, we know the equation. I'm going to kind of write overall below. A sub t equals r times alpha. So whenever you have an object that is spinning faster or slower, you have an alpha. And whenever you have an alpha, you also have an A sub t. That is a linear, that is a moving faster or slower. So whenever you have one, you have the other. If you have an object that's spinning at a constant speed, both of those are going to be 0. The one you always have, though, is a centripetal acceleration. A sub c equals v squared over r. That would be something like a rock is stuck in the tread of the tire. It will have a centripetal acceleration because it's changing the direction of its linear velocity. and this velocity is the tangential velocity, and then you have a centripetal force along with that. Remember, centripetal means center directed. When you have a centripetal force, that's always going to show up through Newton's second law when you have a centripetal acceleration. So an F sub c is never something you're going to draw on a free body diagram. It is always a second name given to other forces that are there. So that is an overview basically of everything rotational. Ponder physics.